Hello, everyone. This is my attempt at recording while I still remember everything. I wanted to do this with Panopto like I normally do, but Blackboard is down. Right? I'm gonna email myself this video. Hopefully, I can get it on my phone. I have the app there. Um, this is what I get for putting it off last minute, honestly. I deserve this. But I thought it'd be fun to check this out. This is the snipping tool on Windows 10 or Windows 11. I don't know. It allows you to do screen recordings with audio. I thought that was awesome. Um, so you're not going to be able to see my face. I'm not going to be able to do my hand gestures, but we'll see if we can get through this. Let's get into it. Oh. Let me do it? Okay, cool. I guess I have to click. Okay, so we're talking about the special census today. Um, the census generally right now, but we'll get into the special census later. So we have a bunch of receptors, and they tell our brain what's happening. Otherwise our brain is a pile of meat in a tank. Nothing's getting in or out except through these sensory receptors. They are I like to say perception is reality. Although I know if you have some uh, mental mental difficulties, then that may not necessarily be true. But generally, yes, perception is reality. So there's a specific stimulus, like let's say it's quite cold in this room. I'm not wearing socks. My feet are touching the bare tile floor. My feet are cold. There are thermoreceptors in my skin that will say, "Hey, it's cold," and send that message to the brain, and on and on and on, and all of China knows you're here. Um, the different sensory receptors have what's called a receptive field. They might have a large receptive field, like on the less sensitive parts of your skin, like the top part of your forearm, or the back of your neck might be a little bit more sensitive, so the receptive fields will be a little bit smaller. Um, there's this thing called the sensory homunculus, and I'm not sure why I didn't include that on. Oh, no, actually, I know why. It's freaky looking. If you want to look it up, look at the homunculus sensory model. It's crazy. It's a human person, but the parts that are more sensitive are larger. It's on like kind of a rotational, it's kind of on a circle like this, and it goes, the feet are super huge, and then the legs less so, and then other places are really big, like your hands, and then it goes upwards, and then just like the face is enormous. That is it's worth a look. I didn't want to jump scare you, although there will be plenty later. So different receptors respond to different stimuli. So we have olfactory receptors. We have baroreceptors. These are the things that tell us about pressure, blood pressure, your tummy full, your lungs, breathing in. Probably what you did after that midterm, no? And that tells us when our lungs are full or empty, or all that changes in that, as well as olfactory receptors. They tell us whether or not we've lost our sense of smell and we need to go get tested for COVID. The touch receptors, those are in our skin. We get to feel, we get to go outside and touch grass. Auditory receptors, we get to hear our own pulse reflected in the shells. We don't actually hear the ocean, but it's a fun thing to think about when you're a kid. Then there's taste receptors. Those are mostly in your tongue. There are some in your throat, and they can also like help you taste like water. This is a pumpkin spice latte. I like them. Shush, it's not that serious. We've got proprioceptors, which tell us where we are in space. If you've listened to one of my videos before, you know that proprioception is not one of my strong suits. I constantly bang into stuff that I should definitely know is there, like door handles, shopping carts, and I get bruises pretty much anywhere because, I just full force whack. But yeah, this guy knows where he's at in space. And they also tell mechanoreceptors. That's what I wanted to say. Mechanoreceptors. And visual receptors. They help us see this whole presentation. They help us see colors, light and dark. Cool stuff like that. So there are, in general senses, like thermoreceptors. Those are everywhere in your body. They get. We have more cold receptors than we do warm receptors. We have cold and we have warm. Uh, we also have nociceptors. Nociceptors are what go off when you step on a Lego. Those are our pain receptors. These are free nerve endings that are just kind of dangling. Although some of them, like our corpuscles, like remember when we talked about the skin, there's the Meissner's corpuscles, the Pacinian corpuscles. We didn't really get into the Ruffini corpuscles, but they're basically the same sort of thing. They tell you about pressure, and they're sort of lamellated like this. They've got layers. But yes, nociception, thermoreception. And then we've got the special sense organs, like the auditory. Well, special senses require special sense organs. For example, the auditory sense, it has the ear and the structures therein. Then we've got gustation, which just uses the tongue and the taste buds thereon. So these are the 5 senses we're going to be talking about. We've got sight, smell. You should maybe wash that shirt. Taste, auditory, and balance, equilibrium. These are in the same place in your body. You know, you hear, but also the stuff that helps you hear also helps you know generally, oh no, where you are. Helps you keep your balance so you don't just randomly fall over when you're walking or when you're doing this incredibly difficult pose. My goodness. We're going to talk about olfaction first. Olfaction is just the science word for smelling. Excuse me. I'm sorry, that might have been super loud. So this is the nose. It's not just in here that we smell. It's actually all the way in here. These turbinates function to help circulate and mix the air. This nasal cavity here helps warm and condition the air for when we're breathing it. But for now, we're going to focus on smelling. So there's mucus all up in here. If you've ever blown your nose, you know that. And the mucus helps catch volatile compounds, which are actually what we smell. So that, say you're walking through the mall and you pass by a Cinnabon. Whoop, the beautiful cinnamon smell is going to come right up here. It's going to whoosh around the nose and bind to the mucus where the olfactory cells are waiting in this epithelium over here. It's the cuboidal epithelium, if you remember right, because it makes mucus. It makes stuff. It's cuboidal. Yeah, let's go. Oh yes, the opening of the eustachian tube goes down into the pharynx, just the same as the air. So that's why they have you cover your mouth and nose with a mask if you have a cold, if you're sick, because when you inhale the air, it all goes to the same place. It still goes to your lungs. Boop. So this is the olfactory pathway. So delicious Cinnabon goes up into your nose and into these olfactory cells down here in the epithelium, and it connects to the olfactory bulb, cranial nerve 1, remember, and then it goes all the way up into the thalamus, right here, where it is further processed and colored by emotion. It's cool. Gustation is the sense of taste. And it's not just like taste exactly. I don't know what I'm saying. Don't listen to me. This is a goose from the Entitled Goose Game. It was a very fun little game. If you have a Nintendo Switch, I highly recommend it. Although I think it's also on Steam. You play a little goose, and you're kind of a bastard. You just steal people's lunches. What you do with this is you put it in the lake. There's an achievement where you have a little picnic. Hooray! It's a lot of fun. So there's taste buds. We know that. They are called fungiform because they look like little mushrooms. Um, folate papillae. Foliate papillae. Those are the ones on the sides of your tongue. The filiform are the very, very small ones between the fungiform that you can generally see if you stick your tongue out in the mirror. Bleh, you can see those. The circumvallate papillae, you normally can't see those. Um, this These are responsible for the taste. So there used to be like a map where it would say like you can taste sweet things over here, you can taste sour things over here, you can taste bitter and salty. Ooh, fun fact. Sodium helps unlock your taste buds. So when I had COVID and I couldn't taste anything, oh my god, I love food, and not being able to taste like this beautiful roasted garlic, which I know must have smelled incredible, but I couldn't smell it. Oh, I was so sad. The way I could taste anything was putting a little bit more salt on it. Now, a lot of salt's not good for you, but that's why a lot of junk foods and microwavable foods, like convenience foods and stuff, have a lot of salt that helps you taste that stuff better. Also, why monosodium glutamate works so well, because we've got the glutamic acid that has been bonded to the sodium. So um, glutamate helps things taste better. It's in tomatoes, mushrooms, grapes. If you don't see monosodium glutamate on the list of ingredients, and you see one of those other things, it's got monosodium glutamate in it. You might see it as like tomato powder. But yes, this is where all the magic happens. Then there's the fifth flavor, umami. Oh yes, the map. Yes, it's a word I won't say here because it's not professional to say here in an academic environment. But I don't agree with it, and the science has proven that like you can taste all the tastes everywhere, sour, all this stuff. Then there's umami, which is the flavor of meat. And, mushrooms have umami as well. It's just this kind of nebulous other taste. Monosodium glutamate is the taste of umami. I learned the hard way you can't put it in sweet things. My gosh, the RIP, that batch of pancakes, it was disgusting. But yes, it helps foods taste richer, better, but only if they're savory. So this is the taste bud. A single one. Just one. Because look how many you have. These are circumvallate papillae. They have, they invaginate. There's little pockets sort of around it to sort of increase the surface area. Back here is where you can taste water. That's fun. These aren't taste buds. These are tonsils. They're part of the lymphatic system. We're not going to talk about it. This is the epiglottis. This is part of the digestive/respiratory system. It prevents food from getting into places it should not be. Single taste bud, here are the nerve cells, the gustatory cells, and a lot of these senses require hairs. The one that doesn't is vision, but little, very sensitive little hairs, not like the keratin hairs that are on the top of your head or your armpits. They're very, very small sense organs that trigger the sensation of taste. It goes from your tongue through the vagus nerve, the glossopharyngeal nerve, the facial cranial nerve. Actually, so what we know is taste goes through the facial nerve. The glossopharyngeal nerve helps with swallowing and all that stuff. But all of these nerves are affected. It goes through the pons into the thalamus, where a lot of our sensory information is collected and processed. Sorry again. Eye stuff freaks me out. I remember watching Tim Burton's Alice in Wonderland, and there's this little scene where like a tiny mouse stabs someone in the eye with a tiny sword, and I'm like, oh no, hate that. I'm also not so great with eye contact, surprisingly. So we think of the eyeball as part of the eye, but there are other structures that help the eye function. There's the eyelid, helps prevent stuff from getting in there. We've got the lacrimal gland that keeps things nice and smooth. It helps the eyeball move around a little bit. There's muscles. I think I have that on another slide. I'm not sure. The lacrimal gland produces tears, and they go through bloop 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 through the lacrimal pores. And if there's an overflow, that's what crying is. If there's enough that don't get used, it goes through here, the nasolacrimal duct, and that's why you snot when you cry. Bloop, bloop. The eyelashes also help keep debris out of your eye. Although for me, eyelashes get in my eye more often than they help me. Although you only notice when things go wrong. You don't notice when things are working perfectly. The iris is actually a muscle. Well, it lets light in and out. We'll talk about it in the next slide here. But those are some of the accessory structures. So your eyeball is kind of like a water balloon. It's hollow-ish, in the same way that a water balloon is hollow. It's full of stuff. Up here in the anterior cavity, we've got aqueous humor, and over here in the posterior cavity, we have the vitreous body, which is made up of vitreous humor. So it's it's the water inside the water balloon. I'm trying to think of something else, because anyway, we continue. Oh, it's like a cupcake batter in a cupcake tin. It holds the cupcake wrapper out. It fills it up. It takes up volume and space. It's not just it is squishy, but it's not like a liquid. It helps keep the cornea and the pupil supplied with blood, and does all the liquid exchange stuff that blood that's not blood does. It's got different layers. It's got an outer layer we call the sclera, which is the dense regular connective tissue. Then we've got a middle layer. It's the neural layer. That's where the yes. Gosh, this is not really clear. Well, we've got an outer layer, an inner layer, and an even more inner layer than that. So the vascular layer is next. It supplies everything with blood, and then we've got the neural layer. Oh, okay. Yeah, I just talked it through it. What's this? It's fat, holding your eyeball in place. I told you. I told you a while ago. Oh my god. Okay, so here are the muscles. There's the medial rectus muscle. It helps you look down. Up here, we've got the lateral rectus muscle. It helps you look up. And then there are muscles that help you look that way and that way. Toward the midline, away from the midline. So, the iris is not a muscle itself. It's more like a diaphragm. And here we've got the ciliary muscles that pull on the iris to make the aperture or opening in your eye larger or smaller, to let in more or less light depending on the time of day, depending on lighting conditions. And they also pull on the lens to help focus things that are further away or closer. It changes the shape somewhat, not too much. The cornea helps protect the opening, because if this was just sort of out in the open, it'd be harder to, number one, focus. It helps. Let me see. So the cornea, all of these things have epithelium if they're in a thing. If there's free space, there's epithelium. So the cornea acts like immersion oil for a microscope. You add a little bit of oil to the slide, and it helps you see better. There's different there's one very specific objective that's very, very powerful, but it needs liquid assistance to focus, and that's what the cornea does. It helps keep the aqueous humor there in front of the lens, and it helps with that. It also protects the open. We've got the sclera. It helps as a docking point for all these muscles. We've got the superior rectus that lets you look up. Lateral rectus. Oh, I got these switched up, but these let you look side to side. This one lets you. The inferior rectus lets you look down, and the inferior oblique down to this side. So there are different structures. There's the iris, which we talked about a little bit earlier. It's like a diaphragm. It lets light in or keeps light out. Ciliary body helps change the shape of the lens there. And the choroid. Choroid's the vascular layer of the eyeball. We talked a little bit about that. Ciliary body changes the shape of the lens so it can bring things into focus. There are even smaller structures in the epithelium in the neural layer. There are rods and there are cones. Rods help see, they help us distinguish light and dark. We have more cones than we do rods. The eye is sort of shaped like a cup a little bit, and there are more cones at the bottom of the cup than there are at the sides. This lovely little creature is the mantis shrimp. He's got 16 kinds of cones. And it used to be an internet meme where this guy is just like, this guy has knowledge of the cosmos that we could never even see, but we only have 3. However, with our big, beautiful human brains, we can distinguish between shades of colors. The mantis shrimp doesn't really need to see shades of colors. Seeing colors underwater is different because of how the light waves are dispersed underneath the water. So we now think that these 16 different kinds of cones help it see different shades of colors. Not that it can see like magic colors that we can't see. The retina serves as the dark room. It's the pigmented layer to help develop the images that we see currently. Back before digital photography and printing, this is how photos were developed. If you exposed them to light before the chemicals set, it would totally ruin the image. They'd be overexposed. So the retina is the neural layer, and there are different structures in it. Of course, it's anatomy class, we're talking about that. Talked about that. The macula lutea. That is the all cones. It's got the highest concentration of cones, and in the macula lutea, we have the fovea centralis. It has the cones are there. We have the optic disc. It is where the blood and the nerve come into the actual eyeball. It's where it connects to the little string. If you've ever seen a movie where someone's eye gets removed, that's the string. The blood and the nerves, they go through the optic disc. So it's got nothing to actually like see with, so we call that the blind spot. Yep. Lens light enters through the pupil, through the lens, and the image is displayed upside down and on our retinas, and it is sort of reconfigured, discombobulated by our brains to the right side up image that it actually is. Excuse me, I'm still sick. So this is the visual pathway. The left and right visual fields are seen by both eyes, but they go to separate different parts of the brain. They both go to the occipital lobe and the primary visual cortex. So through there, through the optic nerve, through the optic chiasma, which is here. There's a few other structures that are very, very close to here. It's the brain. Duh. We're going to talk about hearing. I think this is my last thing. Yeah. So the ear has it's classified in three parts. We've got the outer ear, we've got the middle ear, we've got the inner ear. The outer ear helps collect the sound. Fun fact about the barn owl: its whole face is the ear. It's got little eardrums here and there, but this whole structure helps catch the sound, much like the human ear, and funnels it. Owls have very, very good hearing. They can hear mice scrabbling around in the field, and their wings are utterly silent. It's super cool. Yes, their face is an ear. The middle ear helps amplify the sound, and the inner ear helps take that amplified sound and turn it into action potentials to the auditory processing areas in our brain. So it goes from actual sound to brain impulse very, very quickly, actually. So we've got the structures of the outer ear. We've got the auricle. This is a wood ear mushroom. It looks like a human ear, but it's a mushroom. It collects the sound, like I said. The external acoustic meatus is the tunnel. It's the it's where you're not supposed to stick Q-tips because you can push the cerumen or wax into the tympanic membrane, impacting your hearing. The tympanic membrane is the first sort of it catches the sound, it makes it louder. Have you ever been on an airplane? Your ears will pop if there's like a change in elevation, and the change in elevation is the eustachian tube popping back open. It closes under pressure. We've got the hammer and the anvil. Those are the first two bones. So the hammer is directly connected to the tympanic membrane, and the anvil it goes bam. It increases the sound, and then we've got the stapes, which is Latin, I think, for horseshoe. So, hammer, anvil, horseshoe, which is connected to the oval window, which is connected to the cochlea. This is a thunder sheet. Back in the day when we didn't have like electronic sounds, whenever we wanted to have thunder in a play, someone would take a hammer and go whoosh. Then there's the round window, which is on the cochlea, and it just helps release pressure, as does the eustachian tube. It also empties excess fluid into the pharynx. That's why there's ear, nose, and throat doctors. It's all connected directly, and the health of one impacts the other. I think this is my start of the inner ear. So the cochlea, I think it's shaped like a snail shell, like a seashell. These are fossilized ammonite shells. This is the primary actual organ that does the hearing part. It's connected to facial nerve 8, the vestibulocochlear nerve. Your ears help you balance. I know that sounds weird, it sounds untrue, but it is. We're gonna go into the actual structures. So we have the semicircular canals, and they help you determine what's going on where in the position of your head. The anterior duct helps you determine up and down motion. The posterior duct detects side to side motion, but side to side like this puppy, all the way to the side. So if you're laying down, the posterior duct will tell you that you're laying down. The lateral duct detects motion from side to side like this. And in the vestibule, which is slightly to the side of the semicircular canals, we have two structures, the saccule and the utricle. They both detect gravity, but the saccule detects vertical motion, vertical acceleration, and the utricle detects horizontal acceleration. Equilibrium is basically our sense of balance. It's just keeping us in one position instead of like a rag doll. We've got static equilibrium, which, just helps us maintain our posture as I'm recording this video, as you're ignoring this video, as she's knitting this, I want to say scarf. Then we've got our dynamic equilibrium with the semicircular ducts that tells us where we are, where we're moving, how we're moving. Yeah. There's different steps to hearing. It has to go through your headphones, into your ear, through the external acoustic meatus, into the eardrum, the tympanum, through the ossicles, into the cochlea, and through that, through the auditory nerve, through the pons. The pons helps process sounds. Into the auditory receiving centers, the I want to say it's either the Wernicke's or the it's the Wernicke's area. Yep. Through the external acoustic meatus, it's the hole in your skull. The speed of sound is 767 miles per hour. So it's really fast. We don't really think of air as matter, but it is. Sound has to travel through matter in order to get to us. And that's it. Hooray! We're done. Hopefully Blackboard will be up soon, and I'll be able to see all of your wonderful presentations. Have a great night. Bye-bye.